where we left off on Tuesday, or at least approximately here. We were talking about magnetic field and the fact that we could define magnetic flux as well. This is where we landed at the end of class on Tuesday. We had just finished talking about the fact that magnetic field exerts a force on moving charges, and we figured out how that worked, and we expressed it with our cross product. Whoops. I can't draw anymore. Why can't I draw anymore? Well, that's not what I wanted. Why can't I draw? Hold on. Need to be able to draw. Mhm. Okay. One more time. There we go. And we expressed the force so that things are consistent. We express the vector force exerted on a moving charge by a magnetic field as the cross product of the charge's velocity with the field. That's kind of where we landed on Tuesday, and we had sort of discussed the fact that this says or current, and at the time I claimed that it made sense because current is really just moving charge. So if the magnetic field exerts forces on moving charges, it should, I think, make sense, exert forces on current as well. But we didn't say much about that until today. And here's this slide, which is this is one of those slides that this is a perfectly well-defined picture. We've got a magnetic field into the page. We see the X's, that's the arrows, the fletching on the back of the arrow that we launched away from us into the page. We've got the drift velocity of a positive charge carrier up the page. And if we do the right-hand rule, V cross B, the force points to the left on a positive charge carrier. Now, the deal with that, the drift velocity is what it is because the charge carriers collide with the molecular lattice of the conductor. Right? There's a net motion up because there's like a random thermal motion bouncing around, hitting the different sort of fixed pieces of the molecular sort of crystal structure of the conductor. So exerting a force on the moving charge carriers, when those charge carriers collide with the physical sort of lattice structure of this wire, that force is going to, like, there's an impulse associated with that collision that is directly resulting from the force on the moving charge carriers by the field. So exerting a force on the moving charge carriers essentially means exerting a force on the whole stupid wire. What force is that? And here's a fun expression that is not clear at all where it came from. At least not to me. It was like, that's confusing, and I have no idea why it looks like it does. And then from this slide, the next thing they show us is this, and the next thing they show us is this. It's clear enough that this picture is the same as this picture. But what does that have to do with this picture? And what does that have to do with this? These are great questions. You guys remember Bill Nye, the Science Guy? Yeah, right? It was good shit. Bill Nye, so somewhere during the show, Bill Nye had a segment that was like, there was an introduction to the segment, and it was like Bill Nye's face making thoughtful expressions, and it was, please consider the following. So here we are. Suppose we have a wire of circular cross-section in which there is a current flowing such that we can define a current density vector. And we did do this back in when we were discussing Ohm's law, current and EMF. We talked about current, and then we talked about a vector, current density, that talks about the charge per unit area that we're moving per unit time in what direction. And we said it's the current per area in the direction of the, well, shit, in the direction of the drift velocity. Okay, cool. So there's that. The current, remember, is the charge per time. Now, the charge that moves for a given amount of time is some small number of electrons. So I've got E, the charge on an electron, and if we knew how many of them moved, that would be the total charge that moved in some amount of time, dt. So this dn is what I'm using to express the small amount of electrons that are moving through a particular cross-sectional area, let's say, in some amount of time. Now, that has to do with how many electrons were within sort of striking distance of that cross-sectional area. In other words, we're talking about some cross-sectional area here, and we're looking for the number of electrons that go through that in some small time. But that means we need to know how many electrons there were in this sort of cylinder able to get to that cross-section in time dt. What we're talking about now is a volume. So we're interested in the concentration, the volume concentration of charge carriers, and the small differential volume. That's how many altogether there are in that space. And then E divided by dt. Now, the differential volume, the cross-sectional area is the area. Like it is what it is. It's constant. So we're interested in the length of that cylinder that we're traveling through in time dt. If the electron was to the left of that sort of shaded gray cylinder, it wouldn't get to the cross-sectional area that we had in mind in time dt. It wouldn't get there yet. So volume, area times length, and dx dt, that gets us the drift speed. This was an equation we wrote before, except instead of E, we probably wrote Q because we were talking about general charge carriers. Here I'm talking about electrons, but that's just out of habit because I know that the charge carrier in a metal is an electron. Okay. So I want to go back, think about the current density. The current, I, is this whole expression. Little n, capital A, drift velocity, charge on an electron. Current density J divides by area. So the area cancels, and we just have that expression. Now, little n is the concentration. It's the volume concentration of number of charge carriers per unit volume. This V in the denominator there, that's volume, not volts or potential or anything like that. That's volume. I should probably edit that while we're here. Now, the number of capital N, the number of electrons, times E, the charge on an electron, that's Q. That's the total charge Q moving with speed, drift velocity V. So this purple circle, capital N drift velocity E, that's QV in our QV cross B formula. Total charge with what velocity? That's what we're saying. Okay. Now, if we solve for the thing that's circled in purple here, it's the current density J times the volume. But the volume is, again, area times length, where in this case, we're talking about the entire length of this particular wire. So here, L is a vector from one side to the other in the direction of the current density. So that's this down here. The total charge Q altogether is related to the current density and the total volume. And it's all moving with speed V. So we get to talk about QV cross B. Current density J is current divided by area. Volume is area times length. And if we decide to write that as length as a vector, because, well, frankly, because I need this thing in purple brackets here, purple parentheses, I need this to be a vector. Otherwise, the cross product doesn't make any sense. A could be a vector. but it's going to cancel. We've used A as a vector before, but it's about to cancel, so I don't want to use that. And current is strictly defined scalar. Okay, so let's use L. Let's talk about vector L. Along the wire in the direction of the current. And then we can write the force due to the magnetic field as the current magnitude times the length vector cross the field. We've seen that equation before, but only for a second, because it's where we left off. Here. Where did they get that equation? That stuff we just said. And that stuff we just said, that's related to this stuff here. I just thought it would maybe be worth looking at a little bit more closely. All right. It's a cross product, so it works just like all the other cross products. We orient our fingers in the direction of L, we curl them into the direction of B without breaking our knuckles, and our thumb points in the direction of force. And this trick works, by the way, no matter which direction we're thinking about for current. If we're thinking about positive charge carriers, then the current flows in a particular direction through the wire. And so we orient our fingers in that direction. If we're thinking about negative charge carriers, the current actually flows the other way, and we would orient our fingers the other way. And that gets us the minus sign of, the difference between positive and negative charge. So this expression works whether we're imagining positive or negative charge carriers for the current. L is in the direction of the current, which is determined by whether we're talking about positive or negative charge carriers. So this is going to be true regardless. Okay. So hopefully we feel a little bit more sort of familiar with the cross product going on here, and with the idea that a magnetic field interacts with the current in a wire, according to this expression. Before we go further with magnets, I'd like to remind us of a thing from way back in our first unit on electric fields and charges. This slide was presented identically in that particular lecture, with the exception of the word electric with an exclamation point, because we were talking about magnets, and here's a slide about electric dipoles. This was a thing that we sort of talked about, but not very much. I sort of justified that we were going to represent this with a dipole moment vector P from the negative charge to the positive charge, but I didn't really explain why. And I didn't really cover, I don't think, where this equation comes from once we do define that. It's going to be useful to do that. So I thought I would take a minute to unpack this slide, because frankly, I think the electric charges and their forces are more familiar to us still than magnetic forces and fields, because, well, we've been dealing with electric fields and forces longer than we have magnetic fields. So let's use this as kind of a springboard for what we're about to say about magnetic dipoles, because every magnet that that's what we said on Tuesday, every magnet is a dipole. The fact that the compass needle rotates in a magnetic field, that's torque. So we're going to have to talk about the torque on a magnetic dipole. It's just, I think it'll make more sense if we start with sort of really digging into the torque on an electric dipole. So a picture. We have let's think of this as an electron and a proton, or you know what, even better, an electron and a positron, so that they have the same mass. We've got an electron and a positron, and this thing exists held together Okay. We've got an electron, some sort of negative charge, and some sort of positive charge, and they exist held together by a rigid bond. Suppose this is, I don't know, a water molecule. So there's a net positive side and a net negative side, and those two sides are held in relation to each other by the covalent bonds that are sort of holding the molecule together. So the orientation of positive and negative and the spacing between them, that's not going to change. They're held together by a massless, rigid bond. So we could think of it like a barbell with two charges on either side and a rigid thing that we can't bend. Okay, the force on the negative charge and the force on the positive charge both have magnitude QE, where E is the electric field that is uniform in this region and points to the right. So the net force, because the force on the negative charge is opposite the electric field, the net force on this object is 0. So we've got a thing in translational equilibrium, but the net torque about if these, the net torque about the center of the bond is not 0. There's a torque possibly due to the force on the positive charge and one due to the negative charge. And they both tend to rotate this sort of object clockwise. In our convention, that's negative. Lost a minus sign. Okay, so we write them with negative signs, and remember that torque is lever arm cross force. The size of the lever arm is half the distance between them, which I have called L. The force is QE, and then we need the sine of the angle between them because it's a cross product. So, and there are 2 of those. So we end up with this expression. Now, I look at that and I see a thing that has a magnitude. Length, charge, electric field, sine theta. And that sine theta makes me think about cross products, which is no accident because it came from a cross product. But if we look at the cross product that it came from, the force, suppose we wrote it as QE. This is not really an equal sign. The force on one charge is QE, the force on the other one is QE. It's just Q is scalar. So we could multiply either vector, like scalar multiplication, we can do it any time. It's commutative. So if we multiplied QR cross E, that would get us the same result. But that, I look at QR and then I look at QL and I say, well, we're doing that. We're doing that cross product. This is a thing that's going to rotate clockwise, which is a negative torque in our convention. So the fact that this minus sign is there, that's just because we're going to rotate clockwise. The magnitude of a torque would be the magnitude of the first part, LQ, I guess, times the magnitude of the second part, E, times the sine of the angle between them. So let's give that first part a name. Let's define it as an electric dipole moment. I wanted to make that this color, the color of the definition. And I'd like it to point from negative to positive, which is kind of opposite the way we normally think of electric field. Electric field points away from positive and towards negative charge. So for this definition, we've got the other way. It's like an internal thing, internal to this bond. QR, where actually the length of R is L. It's the whole size of the bond. And you could think of it like the positive charge is L over 2 away in that direction. And then the negative charge is L over 2 away in the opposite direction, but it's a negative charge. So those two opposites cancel out and we just end up adding. And we've got the magnitude Q times the length between them oriented from negative to positive. If we make that definition, then we can take this expression and rewrite it that way. So that's where that torque equals electric dipole moment cross E comes from. Hopefully, this slide makes a little bit more sense now. Suppose, now, okay, put electric aside and let's talk about magnetic again. Suppose we have a loop of current. I don't like the way this particular picture is labeled, but I liked the orientation of it. I've got to fix it. I'd like to represent this with vector L and scalar I. Current is scalar. I like the textbook this came from. It actually didn't come from Pearson. This is from McGraw-Hill, the picture anyway. I like a lot of the choices that textbook makes. I'm not a huge fan of this one. Current is scalar, and I don't want to sometimes have it be a vector. That's weird. If current is scalar, current is scalar. Let's leave it that way. Okay. If this orientation is fixed but free to rotate around an axle, then let's talk about the FB equals I L cross B kind of force that we were just examining. If we talk about, I don't know, path one, leg one of the square, or I guess the rectangle, the current is magnitude I. The length vector in the direction of the current points this way. And the magnetic field points up. So we've got I kind of that way, and we curl our fingers into the direction of the field up, and my thumb points that way. If we look at path 2, we do the same thing. We've got the current flowing this way, magnitude I, length vector L, goes up the page at an angle, curl the fingers so they're coming out of the page, and my thumb points that way, parallel to the axle. You might be able to see if we go path 3, path 4, that we've got a force this way and a force this way. Now, if we rotate the thing and look end on, so we hold up the things so that path 4 is right in front of us. And as we go, we've got, if we follow the current comes around this way. So we see here it's coming at us on this side, and here the current is going away from us into path 1. So that's what we did. We held it up, and it's stuck on this axle. Like I don't know, there's like a washer here, and it can't move back and forth. So the forces on legs 2 and 4 don't get to do anything. The forces, well, plus they would cancel anyway. The forces on legs 1 and 3 also cancel, except if we have this loop at some angle, which should start to sound familiar, there is a net torque about the axle. All right. Let me go back to the notes. Same picture. I drew a coordinate system so we can isolate angle theta. The length of leg 4 is marked W. I've drawn it in orange, and I've used orange to indicate the measurement demarcation. Forget what to actually call that. So we're holding side W up in front of our face. The force that acts on leg 3, which is in our left hand as we're doing this, is to our left. The force that acts on leg 1, which is in our right hand, is to our right. But there is a net torque about the axle. From the axle out to the point of action of the force, that's W over 2. That's the magnitude of the action distance vector, the lever arm vector. The force has magnitude, well, they've written it as F sub m, lever arm, force, sine of the angle between. The angle between is marked as theta, so we're good there. We know the magnitude of the force. It's ILB, where L is the length of the two sides that we're holding on to. I guess we're not actually holding on to them, but they would be in our left and right hands if we did hold on to them, because we're going to hold on to them. But anyway, you know what I was talking about. So we've got two of the same term, IWLB sine theta. Now, WL, I want to get a little bit of color coding here. So W is orange, L is purple, and the field is blue. Now, WL, that's the width times the length of this rectangular loop. WL is the area. Of the loop. Okay. B is a vector, and I see a sine theta. I start to think about the cross product and how torque was originally a cross product, and I start to think about the same shit we did for the electric dipole. We had charge times a spatial vector. And here we're looking at current, basically charge, times area, which is a spatial quantity. We have defined area as a vector before. Tuesday, we were talking about magnetic flux, and we talked about how area is a vector. So if we think about area as a vector, then this looks like area cross field times current. Or like length, I guess I'll do it up here. Length cross electric field times charge. So if we defined the charge and the length pieces as a dipole moment for electric fields, there's absolutely nothing to stop us from defining the charge piece times the space piece, current times area, as a magnetic dipole moment. I'll use the symbol mu. So that we can talk about the fact that the torque on a magnetic dipole is as a result of its magnetic dipole moment cross with the magnetic field, just like we had for an electric field. Dipole moment cross field both times. For magnets, we care about current, not charge, and we care about area, not length, but otherwise, same idea. This trick works if we define vector u as the current times the area vector. As you know from your work with the cross product generally, area vectors have, we've got a choice. In the diagram, we drew it this way, but why didn't we draw it that way? And for that matter, why is that hand drawn there? What is that doing there? What does that have to do with anything? And the answer is the same. We choose the direction of the area so that if we follow the current around the loop with our fingers, if we curl our fingers around the loop, in this case, counterclockwise around the loop, our thumb points out of the page back at our face. If we orient the thing so that we're looking at side W and follow the current around, our thumb points in the up direction as opposed to the other way. So we choose the area vector according to, no surprise, according to the right-hand rule. Follow the current. Which way does your thumb point? Use that as the area vector. Questions, comments, concerns? Okay. With all that being said, this figure makes a lot more sense. We drew a magnetic dipole moment vector mu associated with a current loop. But we know that a bar magnet will rotate in a magnetic field. The magnetic field of the Earth points towards geographic north because that is a magnetic south pole. So this north pole will be attracted to it and point north. That torque is exactly the same torque that we were just talking about. Exactly the same torque. Which means we can represent the fact that this bar magnet, this compass needle, torques with its own magnetic dipole moment vector mu, which is drawn from south to north inside the magnet, which is backwards. Outside the magnet, the magnetic field points from north to south. This is the other way, just like we defined the electric dipole moment as the other way, quote unquote, from negative to positive, opposite the usual direction of the electric field. This is great. It's entirely consistent with everything we did before. This is fantastic. So we can write this slide. We can clear away all of the sort of derivational stuff. If we have any current loop in a magnetic field, we can define well, it doesn't have to be in a magnetic field in order for us to define a magnetic dipole moment, mu. Follow the current, your right hand, your thumb points to the left on the page, and that's the direction of the area vector. So it is the direction of mu. If we put this loop in a magnetic field, then we can figure out the torque upon it according to dipole moment cross field, just like we would for an electric dipole in an electric field. Okay, cool. What if we have a magnetic dipole in a field that is not uniform? This is a confusing picture. At least I was confused looking at it just now, because I thought that the front of the loop, the side closest to us, was the other side. If we look really closely, you can see that the field lines pass in front of the left-hand side of that loop, which means that's the back. So we're looking at a circle. Where's a convenient circle? We're looking at a circular loop end on. And the side of the loop that's closest to us, this one, is the side in which current goes up the screen. And then current goes down the screen in the back. Okay, so if we use our right hand to do that, here I am looking at the thing. So in front of me, I see a current up So I hold my fingers this way, and the dipole moment points to the left as advertised. Even though it kind of looks in the picture like it's going to the right, it's not. The current goes up in front of our face and then down beyond. So we follow that with our hand, and my thumb points to the left on the page. So as labeled, the magnetic dipole moment of the loop points to the left. Now, the force on the pieces of the loop, dF, is always perpendicular to the field. The field direction changes, however. Here, the field points out at an angle a little bit, which means there's a little bit of a horizontal component to that force. All of the vertical components, all of the radial components cancel because everything's symmetric radially. But that extra bit along the x-axis, that doesn't cancel. And this particular current loop is pushed away from that bar magnet, which helps explain why refrigerator magnets stick to the refrigerator. This trick works with a bar magnet. This trick works with a current loop, because all we care about is the magnetic dipole moment. We draw the magnetic dipole moment mu in a uniform field. In this orientation, there's no torque and there's no net force, equilibrium. In the non-uniform field, now this is a magnetic dipole moment that points away from the magnet, not towards it. Note the dot and the X. That indicates the current coming out. It's coming towards our face on the left and then back in on the right. So if we do that with our hand, curl our fingers in front of our face from left to right, my thumb points up. So the magnetic dipole moment points up. And what's going on? The field points this way, but the force points down a little bit, perpendicular to it. And so there's a net attraction, which helps explain why if we reverse the magnet, we get repulsion or attraction. If we change the orientation, we change the direction of mu, which changes the direction of the net effect. And we see that we get identical behavior from current loops as we do from bar magnets. As far as their response to external magnetic fields, I cannot tell the difference. If you hand me a thing and don't tell me what it is, and I expose it to a magnet, and there is, in this case, attraction, I don't know for sure whether the thing that you handed me was a permanent magnet or a loop of current, because I have no way of distinguishing them based on their behavior. This is how magnets work. Atoms in the material have their own little atomic scale magnetic dipole moments. In a permanent magnet, the dipole moments of those atoms align. And there's a net dipole moment that we could draw sort of macroscopically on the scale of the object itself. Sure, there are these individual atomic magnetic dipole moments, but if we sum them all, no, it's not it is unmagnetized. It has no sort of macroscopic dipole moment. This one, on the other hand, if we sum up all the little mu atoms, it's not going to be zero. Okay. We can, if we're interacting with a magnetizable medium, like the metal behind the whiteboard or the metal of the frame of your refrigerator, or the metal in this pictured nail. As we expose the atoms of the nail to the external magnetic field, their own atomic dipole moments tend to align. Their south poles tend to be attracted towards the external north, which means their north poles and magnetic dipole moment is drawn from south to north. So we've got a net magnetic dipole moment that way in a non-uniform magnetic field, which means, okay, hold on. Net magnetic dipole moment away from a magnet in a non-uniform field, in a diverging field, I suppose, means attraction. So that nail is attracted to the magnet. If we reverse the magnet, fine, same thing happens. The norths are attracted to the south. There is a net dipole moment to the left, but now the field points in. So it is this situation, but we reverse the magnet, which means we reverse the effect. And instead of repulsion, we get attraction again, which helps explain why a magnet is attracted to my whiteboard no matter which way I turn it. We have a loop, or a dipole oriented in a external field. Now, if we positioned the dipole in a particular way and then let go, the field would exert a torque and the thing would rotate. And it would rotate a torque that causes rotation through an angle does work. Well, okay, so that means that a field is doing work and it's a conservative thing, so we could define a potential energy. Suppose we start in an electric field, E, that is uniform, with the dipole oriented the wrong way. Well, no. Suppose we orient it the right way. The dipole moment points from negative to positive, so it's this way. But what if we go in and manually turn it? How much work do we have to do against the torque that is created by the electric field? In order to take this thing the way that it is and rotate it around like that, we have to do some work. Now the dipole moment and the field are anti-parallel. We did work to put it in that situation. If we let go and technically this is in rotational equilibrium, but it's an unstable equilibrium. If we displace it at all, it'll flip around back to the way that it wants to go. And that technically it's in equilibrium. That's the same thing that happened Tuesday when I was trying to balance one magnet above another due to the magnetic repulsion. As soon as because I can't control it with just my hands, right? It was always going to be in just the slightest disequilibrium. And as soon as it's not in equilibrium, it flips around due to the torque created by the external field of the bottom magnet. This is what we're talking about here, but here we're talking about it for electric fields and electric dipoles. Don't worry, we're going to say the same shit for magnetic dipoles in a second. The work that we do, sure, is force.dl, but it's also for rotational forces, torque.d theta. Torque for an electric field is dipole moment cross E dot d theta. Now, the torque that we need to use, this is the work that we did to move it. The torque that we are using, it's in this picture, it's creating a counterclockwise torque, and d theta, as d theta goes from 0 to pi, is also clockwise. So the torque and d theta are in the same direction. So this is my annotation in orange. Because the torque and d theta are in the same direction, the dot product just vanishes, and we just have the magnitude of the cross product times d theta. The magnitude of the cross product is the dipole moment cross E sine theta. And we're going to integrate theta from 0 to pi. Integral of sine is negative cosine, and we're going from 0 to pi, which is going to get us negative 1 minus 1. So we end up with that. Which, if we talk about magnitudes only, 2 times the dipole moment times the field. What if we only rotated the thing 90 degrees? Completely analogous method, but we would be going from 0 to pi over 2, and we'd end up with 0 minus 1, which would work with the minus out front, and we would have the same magnitude, just not 2 of them. Okay. What I'm aiming for is a potential energy statement, a formula, a function for potential energy as a function of angular orientation of a dipole moment in a field. I started thinking about the fact that work is force.dl, which is now the force, that says we're talking about an electric field, the force is QE.dl. And then I started thinking about moving the Q around, so it's E dot QdL. If we think about that, like in a uniform field, E we can pull outside the integral. And Q is Q. It's just a constant. So we're integrating DL. This isn't particularly straightforward. Like I didn't write this because it's kind of loose. It's not very rigorous, but we can think of it this way. So we're integrating DL, and that's like L, but then we've got QL as a vector, which is the dipole moment. If we wrote it, it would be the work done, which would be equal to the negative change in the potential energy. Here, we're talking about the work done by the field. The field does some work because it exerts a force, on a charge according to the electric field. And if we move things around, that would be the negative change in the potential energy. Now, the negative change in the potential energy, I am saying, is like the integral of all the little changes in the potential energy. So we're integrating one side, and we're integrating the other side. The only differential part is dl, and the only differential part here is du. So if we got an integral of a derivative, they wash each other out. And we can talk about u and l. Like I said, not super rigorous. But then it starts to look like potential energy is the negative of E dot the dipole moment. Now, how do we reconcile that? Because the dot product has a defined thing, and we need to know the angle between the field and the dipole moment. The field and the dipole moment the cosine is positive in this orientation. The dot product is positive. Here, the dot product is negative. If we want to use the dot product notation, and we need this and this to still be true, that from one side to the other, from one orientation to the reverse, we get an amount of work done 2 PE. Here we only have 1 PE. The magnitude of cosine will never be greater than 1. The only way to make this work, to get this to fit together, to use the dot product notation together with our perfectly rigorous work done, we have to choose the arbitrary constant. We have to set the floor for potential energy in the perpendicular orientation. Then the minimum potential energy is negative. That's fine. It's less than 0. So in this orientation, the dot product would be negative, and that's fine. because, oh, I'm sorry. I've got it backwards because there's a minus sign at work here because here I'm talking about the work that we do, and then here I'm talking about the work done by the field. I apologize for that. Made sense at the time that I wrote it, but that's confusing now. Here, the dot product is positive. Let me write it. P dot E is positive, but U, because U is the negative of that. Come on. The negative of that. The potential energy of this configuration is negative. And here, the dot product is positive. I'm sorry, is negative. I'm all over the place today. Dot product is negative because they're anti-parallel. But because the potential energy is the negative of that, it is positive, which helps explain why when we do positive work to rotate it, the field does negative work. The field does negative work, and the potential energy increases. Because the work done by a conservative force is the negative of the change in the potential energy. So if we do positive work against the field is doing negative work, which is increasing the potential energy, which makes sense because we put energy into the configuration by rotating it. If we release it, it will snap back to the other way. So, the moral of the story. This calculation for the two works that we do, changing the orientation, is perfectly rigorous. The change in the potential energy should be 2PE. There's nothing ambiguous about that, and we still have the freedom to choose the potential energy floor wherever we like, in whatever orientation we like. If we don't want to use the dot product, we could say that this orientation is 0 and that any other orientation has positive stored potential energy. If we want to write it with the dot product, then we have to we have to choose it so that the floor is in the middle orientation. We're free to choose it anywhere we like, and I think it's a really nice, sort of elegant expression. So it's worth making the somewhat unusual choice that the stable stable equilibrium is at a negative potential energy, which actually isn't all that strange. Back in 231, when we talked about the stable orientation of like a proton and an electron, two, the like a van der Waals two atom bond. There's a stable separation, and it lies in a potential well. Let me just shoot that over here. Separation distance r and the potential energy of the interaction. There's some minimum in the potential energy. And if we set the potential energy 0 when they are infinitely far apart, which makes sense, they aren't bonded if they're far apart, so they don't interact at all. If we bring them closer together, then there is an attraction, and the system would tend to minimize its potential energy to the point where we end up stuck in a well, a negative potential energy, a bound state. If we want to separate them, we have to put energy in to raise the water level so that the thing floats to the top of the well. We're doing the same thing here. The bound state is the stable state, and it's a negative potential energy. That's totally fine. We're not unused to that at any rate. Okay, but this was supposed to be a lecture about magnets. I got you. Don't worry. Fine. The torque on a magnet, the torque on a magnetic dipole moment in a magnetic field is as we defined it. And so when the torque was moment cross field, we defined the potential energy as the negative of moment dot field. Fine. Let's define the magnetic potential energy of a dipole as negative moment dot field. All of the same stuff we just said will apply again. It is not particularly common for us to talk about the work done by the electric field. Stop. The work done by the electric field on an electric dipole. It's not super common that we have a practical application for that. However, the work done by the magnetic field to rotate a magnetic dipole, that's a thing. That is important, that if we change the orientation of a magnetic dipole, because a magnetic dipole is a current loop, if we are running some current through a loop in a magnetic field, we can get torque to happen, which means we can rotate a thing around an axle. We can run a motor. We can use the torque exerted by a magnetic field on a current loop to convert electric energy into mechanical energy. Up until now, see, this is cool. This is cool. Up until now, we've been able to move electric energy around. We have DC circuits. We can go from EMF to capacitors. We can store energy. And if a thing requires current, we can run it. But up until now, we haven't really talked about the things that require current. I mean, I guess light bulbs maybe, which just as we pass current through them, they heat up and then they light up. But we haven't, like, what else can we do? If we can get the electric energy from the EMF source to the load, to the thing that requires current, if the thing that requires current is a loop that lives in a magnetic field, we can convert the energy that we stored in the capacitor or the chemical potential energy represented by the EMF, the battery. we can, ooh, or the power supplied by our power grid. Whoa. We can just plug in a drill into the wall and use the current that that represents to pass a loop of current through a magnetic field to turn a motor and, you know, drill something. Ooh, this is very, very cool. I don't quite want to talk about the worked example from the Young and Friedman text about DC motors, because the premise of the question it talks about, without defining, induction, which I find crazy. We're going to talk about it. We will come back to DC motors later in a few lectures, a few chapters, I guess. I think it's still correct to call them chapters, even if I'm trying to avoid numbering them according to only one text. But the particular example I'm thinking about is from the Young and Friedman text. If you're interested in looking it up, it's example 11 in chapter 27. So DC motors is the payoff here. Why are we talking about force on current loops? Because we can do shit. Because we can make these otherwise curious, navigation is really, really cool. Compasses are great. We can leverage the natural phenomenological behavior of these sort of fundamental properties, charge and magnetism. We can leverage them to do shit, to do useful things. And that's big news. It's funny. At the beginning of this chapter, we started out just with being really qualitative and really observational. Here are two things that interact with each other, and I don't understand the mechanism by which they interact. If I rotate one, then they interact differently. If I expose them to a different sort of material, I get a different response. And that was all we had said. And here we are saying, that we can pass a current in a magnetic field that creates rotation, converts electrical energy into rotational mechanical energy. The brushes in the picture and the commutator exist to fix the problem that would otherwise just make this thing go from one orientation to the other and back. If we set this up so that we're in the most unstable situation, where the dipole moment and the field are anti-parallel, if we let it go, there will be torque until we get here. We will here have our maximum rotational kinetic energy. And then as we go past it, as we overshoot equilibrium, torque equilibrium, now the torque will be the other way, which will tend to slow us down, and we'll get here, and then we'll go back. There are perhaps applications for an oscillatory system like that. but I don't really want to I don't really want to drill the, to screw drive that way, because I will get nowhere. I'll try to tighten it and then loosen it, and tighten it, loosen it, tighten and loosen it. I want to use one common rotation. It would be great if I could connect this axle to maybe wheels and like rotate the wheels of a car doing this. That's a cool thought. I really don't want to have that go one way and then the other way, because that's a weird like carnival ride, not actually a car. The commutator functions once we get to the point where we would have felt enough torque to be going back the other way, it switches the polarity, changes the orientation of the current. If we change the direction of the current, now once we're here, we can keep going because we've just passed through we're at the maximum potential energy of the reversed polarity situation. So now we keep going and we can maintain a constant rotation that way. So that's what the brushes and commutator are for, so that we can keep a constant omega. Otherwise, it would just reverse direction back and forth. There's one more idea from this particular chapter of Young and Friedman, and I was very interested to discover that the 6 ideas text that I sometimes refer to does not treat this phenomenon at all. Like, it wasn't in the index. I couldn't find it in the chapter, which I thought was very strange. Because it's an important one. It's not particularly like, what's the word? It's not particularly useful. It doesn't really do much for us. It's just a thing that happens. But it's a thing that happens. Our direction for conventional current is wrong. We defined, when I say we, Ben Franklin defined current in the direction of positive charge carriers, because he flipped a coin and said, okay, that's positive. Call them different kinds. How do we know that it's wrong? And what if there were positive charge carriers? It wasn't until the mid-1900s and we started examining semiconductors that we discovered that the effective charge carriers in certain semiconductors are, in fact, the spaces where electrons used to be, which are positive. Holes, we call them. How would we know the difference? Because we've talked about the fact that a current this way of positive charges would be indistinguishable from a current that way of negative charges. Either way, the net charge is that way. Because if we're taking negative charge from here going there, well, now this is positive. So it's like we moved positive this way. There would be no way to tell the difference, and there would be no different response, because we talked about how if we switch the direction, like if we think about F equals QVB for a magnetic field, this motor would do exactly the same thing if we switched both the direction of the current and the polarity of the charges that were representing the current. Switch the drift velocity, switch the charge magnitude, that's a double negative, we get the same force, we get the same torque, we get the same effects. So how do we know that in metals, it's the negative charge carriers, it's the electrons? And the answer is the Hall effect. If a conductor is placed in an external magnetic field at a particular orientation with respect to the current, there is a net force on the charges themselves. Up until now, we've represented that as a force on the entire conductor, but it is also a force on the charges. The total average current density, J sub x, along the x-axis in the picture, is constant, is average constant. But it might be locally different if, for example, all the electrons that were carrying the current were preferentially close to the top side of this strip. Still, there would be we could still have a net motion of charge through the cross-sectional area of the strip, and we'd end up saying that the current density on average is the same, even though the charges are actually sort of concentrated on the positive Z side of the strip. Why would that be? Well, okay, so if the electrons are moving, because they're electrons, they move opposite the direction of the conventional current, so they move in the negative x direction. Their velocity across the field, F, would be down, but they're electrons, so we multiply by Q, and their force is up. So these electrons that are moving feel a net upward force. And yeah, it's true that the entire conductor would feel that force up, I, L cross B, that we've been talking about. But it doesn't change the fact that the charges themselves are also pushed up. And we can measure a potential difference between the top side of the strip and the bottom side. The bottom is at a higher electric potential than the top. After a little while, there is an electric field set up vertically along the z-axis in the strip. That electric field would tend to exert a force down on your average garden variety electron, which would cancel the magnetic force. So this all finds a stable equilibrium with the top at a negative relative to the bottom. So if we have access to information about the relative orientations of all these things, if the top is negative relative to the bottom, well, then the charge carriers must be negative because they're the things that are moving. The stationary atomic nuclei, which are positive, they are not moving, so there's no magnetic force on them. Also, they're stuck in a lattice, so the electric force that is set up by the electrons that sort of preferentially go to the top doesn't really affect them either. So the fact that there are positive charges present in the atomic molecular lattice of this conductor, not important. It's the negative charges that are in motion. And we can recognize that because the top surface is negative relative to the bottom. If we had a semiconductor, say, where the charge carrier was actually a positive charge effectively, they would, now we said a second ago that the forces would all be the same, so there's no way force-wise or torque-wise to recognize the difference. But if we're pushing positive charges up, which we still would be, now the top plate, like the not the top plate, but the top of the strip has more positive charges than negative charges, and the polarity of the Hall voltage is reversed. I think this is fascinating because for as much as I like kind of poke fun at the fact that Ben Franklin flipped a coin and got it wrong, how do we know? How do we know that he got it wrong? How? Because I've never seen an electron, have you? And I've certainly never seen one move. How do we know for sure that in a metallic solid, it's the electrons that are moving? It's this Hall effect. Edwin Hall observed this effect while still in school, still a student. So don't ever think that the like curiosity and the research that you do, curiosity you have and the research that you do don't matter, even though, here we are in class.